So we start now with complexity, and as you learn through the course, there are a few different sciences that have contributed to complexity. And we'll start with mathematics. We'll continue with physics, biology, artificial intelligence, even economics. But the most remarkable or the most easy to understand contribution is the one of mathematics. And I go back to roughly 100 years ago when Poincaré in 1903 said sometimes small differences in the initial conditions generate very large differences in the final phenomena. A slight error in the former could produce a tremendous error in the latter. Prediction becomes impossible, we have accidental phenomena. However, he didn't know why and he didn't know when, which had everything to do with the fact that he didn't have a computer, of course, 100 years ago. It took until 1964 that Lorentz, an American meteorologist, found out that indeed complex systems, and now we get to the definition of a complex system, nonlinear dynamic systems, so a complex system is nothing more, nothing less than a nonlinear dynamic system, seems to be highly sensitive to slightly changing initial conditions. If you slightly change the initial conditions, that might really either lead to order or to chaos. A complex system has two states, an orderly state and a chaotic state, right? So there's some chaos theory is not complexity theory. That is something else. Now, I'll show you what it means on a very simple equation. The equation you have here on your transparencies, which that xn plus 1 equals a times xn times 1 minus xn. It's a very old equation that describes the survival of a biological colony. The survival in the next period, n plus 1, is function of a multiplier a, of the survival in previous periods, say 30%, and of the death rate in previous periods, say 70%, 1 minus 30. You multiply 0.7 with 0.3 with 1.4, you get 0.294, and you start iterating. So you get it each time again in the xn value, and you get a new xn plus 1 value. That means dynamic. Dynamic means that the value of today is function of the value of yesterday. So this is a dynamic equation. It is a nonlinear equation, since if you multiply the xn with the xn between the brackets, you get xn to the power of 2, and as you all know, that is nonlinear. So this is the simplest dynamic nonlinear equation that you'll ever see in your life. However, as you'll see in the simulations that we're going to do, it can be completely, or it can become completely chaotic. Now, what happened was that Lorentz, on a slightly more difficult set of equations that you find 3 transparencies further, if you go to the transparency labeled Lorentz curve, the butterfly effect, you see a system of 3 equations with 3 variables. That is actually the Lorentz system with which Lorentz discovered what Poincaré mentioned. We are briefly going to talk about that in a video that you can see in a while. However, I go back to my first simple equation, and Lorentz simulated with that simple equation, and he found out that if he slightly changes one of the values, say instead of 0.3, he uses 0.3000001, and of course instead of 0.7, he uses 0.6999999, that suddenly he'll see chaotic differences. Now, you can watch the video that, by the way, is completely in its 45 minutes on my blog, where you can find the whole 45-minute video. However, we're going to take a little part of that video that precisely shows you that what happens if you start with that 0.30001.